For our last topic in sets, we're going to look at something called Cartesian products. So we're going to define what the Cartesian product is of two sets and show some examples. And we're going to devise a couple models to help us understand Cartesian products and help us with some of the proofs that we're going to see a little later. So in order to understand how Cartesian products work, I want you to think about something else that had the word Cartesian in it from your past, and that is the Cartesian plane. So if you recall, the Cartesian plane had an x-axis, it had a y-axis, and the idea of a Cartesian plane is that you can identify each point on the plane with an ordered pair of real numbers. So if you took a point there, you can see a little point there in quadrant 2. If you wanted to identify what point exactly is that, what you would do is you would look for somewhere on the x-axis that is either right above or right below it, depending on what quadrant you're in. And then you look for a point on the y-axis that is either right, straight to the left or straight to the right of it, and put those two numbers together, and that would tell you exactly what that point is on the plane. Now, if you think what is really happening here from a set perspective and not just from a geometric perspective, each axis could be thought of as a copy of the real numbers, right? X could be thought of as being like the real line, so can Y. The only thing is, instead of having your real line only drawn horizontally, you have one copy of the real line drawn horizontally and one vertically. And each coordinate contains an element from each of these two sets. One is a set of is sort of your horizontal set of real numbers, and one is your vertical set of real numbers. And so what we're essentially doing is we're taking two sets, I guess in this case the same set, two copies of it, right? And then making it into a new set using ordered pairs. So we're doing a lot of what we're doing with subsets and things like that, taking sets that we have and making new sets out of them. So here's the definition of the Cartesian product, which, by the way, can be done with literally any two sets. So let A and B be sets. Then the set A cross B, that's how I'm going to say it, is going to be the set of all ordered pairs x, y, where x is an element of A and y is an element of B. Right? So you can think of the elements in A. Those are all your possible elements that you can use as an x coordinate in your ordered pair. And the elements of B, those are all the possible items that can be used as a y coordinate. So if you're looking for x coordinates, you look in A. If you're looking for y coordinates, you look in B. So as an example, here are two small sets that we can work with just to get some computations down. If I want to find out what A cross B is, what I'm going to do is look at all the ways that I can take an element of A to put in my x coordinate and an element of B to put in my y coordinate. So I'll put the first one of each one. So I'll take 1 from A and W from B and put them in an ordered pair. I can keep the same number 1 from A, and in order to make a different element of A cross B, just put in a different element of B. So I have 1W and 1X. Those both have the number 1 in the X coordinate, but they're different points because they have different Y coordinates. And then we do the same thing with 2. You get 2W and 2X, and then you get 7W and 7X, and that gives you all the possible ways you can take an element of A and pair it with an element of B. Notice that you have 6 elements in that set. And when I say ordered pairs, the order really does matter. If I switch the order, that could ruin the possibility of being in the set. So for instance, 1 is in A and W is in B, so 1W is going to be in A cross B. But if we switch the order and make W the X coordinate and 1 the Y coordinate, that's not going to be in A cross B. It'll be in B cross A. It's not that it's not in anything, it just can't be in A cross B. All right. So of course I'm going to try to help you with a conceptual model, and the model I like the best. Well, I mean, this is my personal favorite. You're allowed to have your personal favorites. Is I call it the Cartesian plane model because it helps us see all Cartesian products visually as a Cartesian plane. So I'm first going to describe this verbally, which may be good for you, may be bad for you, depending on whether you're a visual or a verbal person. And then I'll show you visually what I'm talking about. All right, so remember, A is a set. And every set is sort of contained inside a universal set. So you have A is a subset of a universal set U1, and B is going to be some other set that might be in a different universal set U2. The important thing about this A and B is they don't have to live in the same universal set. They can be in completely different universes. We combine them as ordered pairs. So we can think of A cross B as, I'd like to think of it as a rectangle in the Cartesian plane. And here's how you can do that visually. So you can think of the x-axis as being U1. Now U1 itself doesn't have to be a line. Or just the x-axis sort of represents as a metaphor for what U1 is. The y-axis is going to be U2. Right? So U1 is the universal set for A, U2 is the universal set for B. We let those be our axes. We visualize those as axes of our Cartesian plane. You can think of set A. You know the set A is part of U1, so it's going to be somewhere on the x-axis. I find it helpful to visualize it as an interval on the x-axis. So that is going to be a subset of U1, and the set B is going to be visualized as an interval on the y-axis. That's going to be a subset of U2. And then if you look at everything that's going to be either above or below A, or to the left or right of B, that's actually going to form a rectangle, and that rectangle is going to be the Cartesian product A cross B. So that's going to be everything that's above or below A, and also to the side of B, to the left or right of B. Has to be both of those things. Has to be both of those things. And so if you want to, so that's how you can visualize the entire set. If you want to visualize an individual element, say little a, little b, where the little a is in big A, the little b is in big B, what you can do is you can find a point on your Cartesian plane, right, that is going to be right above or below the element A, right, because it's going to be right above or below the point on the x-axis, and it's going to be across from the element B, either to the left or to the right. Okay, so that's a verbal description of what the Cartesian plane model looks like. Let me give you a visual on that. So remember, we were thinking about U1 as the x-axis. So again, U1 could be any set in real life, right? But if we're visualizing this, it helps to visualize it as an axis. So it's going to be a line, a horizontal line. And then U2, that's like our y-axis. So that's our vertical line. If I want to visualize what A is, it's going to be some subset of U1. For me, again, it's helpful to think of it as an interval. So A is all the elements between those two brackets. And then B is going to be some subset of U2. So it's going to be literally some subset of the y-axis. But again, it's convenient to visualize it as an interval on the y-axis. Now, if we look at everything that is, in this case, both below A and to the right of B, we're going to get the rectangle A cross B. Right, you can see that contains all the points that are both below A and to the right of B. That's a rectangle. Now, if we want to find an individual point, then we take an individual x coordinate, that's a little a in big A, and we can take a random y coordinate in B, so that's little b in big B. And then if we want to find the actual point that visually represents what the ordered pair is, it's going to be right below A and right across from B. Now that's not the only model you can use. This is a model I like too. Actually, this is a very helpful model when you're counting elements in Cartesian products. And in particular, it's helpful when you have a model with a finite number, where your sets have a finite number of elements, or they're sets that are very discrete. They're not easily visualized as continuous things like lines. I call it the shoes and socks models. So suppose you have a bunch of pairs of shoes. Each pair of shoe you can think of as an element of A. And you have a bunch of socks. You can think of each pair of socks as an element of B. Then A cross B is all the ways you can pair a pair of how shall I say, put together a pair of shoes with a pair of socks, right? So you got to wear, I mean, if you're going to wear shoes and socks, this isn't something that I do a lot. I like going barefoot myself. But if you're a shoe and sock person, then what you'll do is if you have a bunch of pairs of shoes in your closet and a bunch of socks, who knows, everybody has their hobbies. What you're going to do is you're going to pick a pair of shoes, you're going to pick a pair of socks, and put those together. And each of those is going to be an element of your Cartesian product. And you must list your shoes and socks in a particular order, right? So in this case, I'm doing A cross B, so I'm listing my shoes first and my socks second. If I was doing B cross A, I would do it in the opposite order. I'd be listing my socks first and my shoes second. But I have to indicate with my Cartesian product which ones I'm putting first, which ones I'm putting second, so I don't accidentally put them in reverse order. Again, you don't want to confuse your shoes with your socks, or else you're going to look ridiculous, for crying out loud. You'll have your shoes on your feet, and then your socks over your shoes, and that may look hilarious, actually, so maybe you actually do want to do that. All right, so now you've got an idea about how Cartesian products work. It's time to look at the activities for Cartesian products on the PDF that's included with the video.